So welcome to IT Lab's webinar series. We've got some great guests here, Andy and Chris. They'll introduce themselves in a minute. I've worked with these gentlemen many years ago. I mean, I can't say enough good things about them. You know, they're brilliant engineers, brilliant software engineers. They work in the embedded space where I come from as well. And we spent a few kind of projects working together as well in the telematics area and the telecommunications arena. And yeah, so I'm really looking forward to learning about AI at the edge. It's an area that I'm very curious about. I've done a little bit of AI at university myself, and I've done embedded work. So this would be a nice kind of convergence of the two. So welcome, Andy and Chris.
Thanks, Tis. Cheers.
Brilliant. So I'm going to shut up now because I can talk for England, and I'm going to pass the microphone virtually over to yourselves and let you go for it. And if anybody's got any questions, please put them into the Q&A tool at the bottom of the tool, bottom of the Zoom tool here, and then we'll kind of filter those into the conversation as we go along. So way to go, guys.
Thanks, Tis. So I'm Andy. This is Chris. I'm from Roedan Embedded Systems. Skip past that one. So today we're going to talk about AI at the edge. So this is kind of a bit of an overview of what we're going to do. We're going to talk about. So I'll start with like where what we're going to demonstrate comes into the development cycle and the importance of doing proof of concepts to work out, to crystallize your requirements and to make sure you're building the right thing. I'm going to give you an overview of the demonstration we're going to do. With some system diagrams and the technology that we've got. We're going to quickly do a demonstration. Hopefully it's going to work all right. We had a bit of a nightmare earlier. And then where we would go from that demonstration if we're doing this in a real development system. We're going to talk about requirements and design and the importance of putting security into your IoT system. Then we're going to go maybe a bit and talk about the future of AI, where it's going, what projects we've been working on recently that are in their very early stages, see where it goes, and then maybe have some questions if we've got time. So we're from Roedan Embedded Systems. We're based in Staffordshire in the Midlands in the UK. We've been formed as a company, the pair of us, since 2010. And we specialise in embedded system design. So we try to finish our development at the air interface, we call it, or the comms interface. So we do cloud-based stuff.
Yeah, so we've worked on basically from right down to the hardware up to cloud-based systems. What our expertise is the sort of lower end of that stuff, but we also do we help to spec out the full system, but then concentrate on the lower end and do the software, electronics, mechanical bits, and we've got all the facilities for doing rapid prototypes and proof of concepts, which we'll show you later on in the webinar.
Yeah. So making enclosures, that kind of thing. But we've got a lot of experience in doing requirements capture, system design, system analysis, that kind of thing as well. So rapid prototyping and proof of concepts is what a lot of our customers want to do. So we usually take it from an idea through to requirements, through to making prototypes, and then maybe they would integrate that with part of a bigger system, or they would take that through to manufacture. Although we've had some recently where we've taken that right the way through to actually production, doing the production, end of line tests, that kind of thing.
Yeah, so I mean, we've worked on various projects, various different domains. My sort of background was telecoms, Ethernet, 3G, mobile comms, and we've worked on similar sort of things and power systems. So for protection of high voltage lines, we've worked on things for finding underground cables. We helped to take from conception right through to just pre-manufacture a thing for detecting cables underground. Lots of telematics devices and remote monitoring of sensors, some automotive things. We've even developed a vending machine that does vends pick and mix, so sweets, and weighs them out. You choose which one you want, weighs them out, and then presents them in a little cup. It's like a sweet machine.
Yeah. So we've worked with big companies like GE, Alstom, Leica, and then we work with small local companies as well. So a full range of stuff really. And the idea, what we bring to this is that we can we can kind of cross-fertilize ideas from different market sectors that don't usually work in that way. So because we've got this broad experience, it helps us to fulfill their requirements really, and design a system that maybe they wouldn't have come up with themselves. Which is why people engage us in contracts.
Which is one of the things about the AI at the edge, because for example, the power systems, there's a lot of intelligence that needs to go into detect when there's problems happening, and some of that thinking can now be done in other systems, which in fact I think the next slide probably leads us into a little bit. Let Andy take over.
Cool. So when I was at university, my professor for the DSP part of the course had a research project going, and it was to do with capturing the EEG waves off babies when they're being born's head. Okay, and we were capturing the signal from that, and we were on a DSP writing a neural net, and then that could detect whether the child was in a distress whilst it was being born. The research project didn't really go anywhere, but when I finished my university course and went into industry, I wanted to implement that in the power system sector, because I thought that would be a great idea. You can monitor the power system. If it's behaving erratically, you can throw some circuit breakers and turn it off. But I wasn't really allowed to do that research project when I started. But in those systems, we had a very complicated device, a node, doing some very, very complicated math. And that device cost an absolute fortune, and it had a very low bandwidth connection back to the overall management system. And as I've gone through my career, it kind of changed, so that when cheap, fast comms connections came into the devices, we changed from doing lots of complicated things on the device to just using that as a data aggregator and sending a lot of data back to a central unit or a cloud device to do all the sort of processing offline, because kind of that was the pattern that was kind of popular back in those days. And the last sort of 5-6 years, as you can see from this diagram, the cost of the processing has come down so much that allows us, and the big data guys have done a lot of the work in developing the neural networks. The power's come down, so we can do lots more complicated stuff on very cheap hardware, and we can also still have that very cheap intermittent comms backhaul.
Yeah, I mean, as Andy said, like the power system things are really expensive, proper industrial processors, they're designed specifically for certain tasks like that. Whereas now we can basically take off-the-shelf hardware that costs, as we show in the actual silicon, for example, is like somewhere in between $3 or $4 each. That can run the same sort of algorithms and the artificial intelligence engines that traditionally would need to be done on a hosted system, like put in the cloud or on your own hosted servers. And the constant in all this really is, as has actually been, the cost of the links between the device at the end and the servers. And although it's cheaper now, it's still quite expensive either in cost or in power to get data from one end to the other. So now that we've got this processing power, we can do some of the stuff that we would traditionally do in the cloud on an extremely low power device, and because we don't need that high bandwidth link, we're saving costs and hardware and transmission costs. So that's what we talk about when we talk about AI at the edge. We're moving that sort of artificial intelligence that we traditionally do in the cloud into low power macros, really. So these are just some of the benefits. So we can use the low bandwidth links that are intermittent. Your device does not have to be tethered to a network for it to still function. You can make decisions locally. So when your network does go down, because networks do go down, as we found out this morning when we tried to make it work, we could still make a decision locally and act upon it in real time, which for a lot of things is important. And the thing as well is you can have hundreds of thousands of these devices out in your network of nodes, all acting independently, but still reporting back and still reporting and requesting information as and when they need to. But they are individual, so they do it autonomous.
So I've got a question, Chris and Andy, around that. So this kind of migration of the compute power going back towards the embedded devices, it kind of moved away and it's kind of moving back. Is that kind of a little bit of a stampede going on, or is it kind of still a trickle?
It's gaining pace now. The tools for doing some of these things are getting easier to use, which I think is the big thing. Cost of the processing power is plummeted. The issue you have is that storage is still relatively expensive. And when we're talking about, let's say, 100,000 of these devices, you want them to still be as cheap as possible. And it's the memory that probably costs a lot of money. That and the silicon to do the radio side. Again, that's coming down in cost. So it's gaining speed, and there's more and more devices that are coming out that we've got security cameras in the office, for example, and these are really cheap. They're $22, I think, to buy these security cameras, but they've got that much processing power now that they're now doing people detection and filtering out things like animals and looking at behaviour of people in the camera itself, and something that costs, say, $22. And they are. That's probably one of the big things that will happen. It's like you're moving the complex stuff into these cheap devices, and as more people do it, the cheaper it gets because the silicon gets cheaper. So.
And then the other driver for this is people wanting things that are battery powered. So if you've got something that's powered off a lithium-ion battery, you can't run a 3G modem up all the time because that takes like hundreds of milliamps all the time, and the battery's just not going to last. So what you want to do is very low power, low bandwidth links, and then that allows you to have a thing that's battery powered that you can attach to a tree or a chimney or whatever you're doing.
Right. Yeah. Yeah. Brilliant.
Okay. So quickly talk about what we're going to demo. So our sort of normal development cycle for projects, we don't have a fixed process. Our clients all, they either have their own processes that they wish us to follow, or they have nothing at all, or they want to do it as fast and as cheaply as possible, and they don't see the benefit. So we're constantly changing how we work. But for this little demo that we'll show you today, we've sort of followed our preferred processor. Now, first of all, gathering all the requirements, looking at the requirements, and then coming up with a proof of concept to see whether what's been suggested is feasible. So that's what we're showing you here. We've gone up to the proof of concept stage, and it's not rough and ready. Yeah.
Right. Okay.
Good description.
Yeah. Right. So I'll tell you what it is. So we made up some user requirements. It's a facial recognition system. We're pretending that it's going to open a door just for people it knows. It's going to be battery powered in case of power failure. It's going to still work if there's no network. It's going to make a decision quite quickly, and it's going to log if it can. Accesses and failed to accesses. So that's the requirements we made up for this system.
We've chosen, because it's a low power device, needs like a battery. So as Andy said, we can't use traditional like cellular modems, and so we do a lot of work with LoRa. So we base this around the LoRa network. It's a wireless technology. The device basically broadcasts out a message, and it's picked up by any sort of LoRa gateway that's in range, fires it into the network, and it comes out in the application. So all of the data is encrypted end to end. So the device encrypts the data, fires it into the network, and it's our application that unencrypts it, so that you can't slip on the data in theory whilst it's being transmitted. It all flows into our IoT platform, which is, there we go.
Oh my God, too far, sorry.
Right, so for this, we basically had some hardware kicking around, so we've gone overkill on the amount of processing power that we've got. But it's still actually really cheap. So the thing that does the facial recognition obviously needs a camera. So we've got this little board that's got a 2 megapixel camera on it. It's got a dual core ARM processor, plenty of storage, plenty of RAM, but it only costs £15, which is around about $20-ish, which then talks to another board, again, which has got actually the same processor on there, but this does the wireless side of it. Again, similar sort of cost. If we're to going past the proof of concept stage, then we combine it into one cheaper device.
And just very quickly, chaps, so you've kind of mentioned the wireless connection there, the LoRa network. I don't know if you kind of covered that a second ago, but I mean, that's, I mean, is that free? Is it kind of a licensed kind of bandwidth?
Okay, so it uses license-free frequencies. We are piggybacked onto a thing called the Things Network, which is a worldwide LoRa network. So there's a worldwide network of gateways which feed into their network. That is free. There are paid-for versions. So, for example, in most countries now, actually, but France, for example, I think on every Orange-owned cell tower they have LoRa gateways, so they've got quite good blanket coverage. Obviously, you pay for access to that network, maybe on message or per byte, but you can actually implement this yourself. Everything is open source. The gateways that we use, we've got one in the office here, there's one at Andy's house, there's one at my house. They link up to the Things network, and because we provide that, then other people can piggyback using our gateways into the network. So it's sort of a community-driven thing. But you can pay for access as well if you want. If you want that 100% uptime, 99.999% uptime. But for demo purposes, we can leverage the community-driven thing, and the cost of entry is really cheap. Gateways £60-70. As you've seen, the hardware is
peanuts.
Yeah.
Cool. So you've got a diagram here of the.
Sorry, Tisha, you're on mute. I think you're trying to say something. Sorry.
I was just going to say that the kind of miniaturization, and the fact that you've got that entire kind of network capability on that one PCB, for me, I find that pretty fascinating. How it's.
We could go quite tech into it.
Everybody interested.
Yeah, it's probably best to maybe for Q&A at the end. But there's a company called Centre, and they basically make the silicon. It's their standard. It's one chip. That handles all of the RF side. So yeah, it is pretty impressive.
Excellent, that's good.
Cool. So just very briefly on the software that we're running here. So on the ESPi, the one with the camera on it, we're running FreeRTOS, which is kind of our go-to free, lightweight operating system. It's not Linux, but it isn't a little horrible scheduler either. It's got some nice features in there. FreeRTOS we choose that because if any of our customers need to go to a safety critical system, there's a thing called SafeRTOS, which is basically the same API. You can just swap out the operating system and you've got a SIL 3 level certified operating system, which is brilliant. On top of that, we've got a library called ESP Face, which does the face recognition and detection stuff for us with the MTNN neural network library inside that. I wrote a little application that sits on top to just be able to add and delete, detect faces, and it sticks whether it's found a face or not found a face over a little serial link to the other module. Yeah,
which then picks it up and then patches it up into a LoRa message and basically pings it out over to the network, which is quite a lot of information on here, so we'll probably just quickly go over this, but it fires it over to the network and then it enters into our IoT platform, which is based around a lot of AWS systems. Because we do a lot of demos, this allows us to quickly add in new devices. I mean, we've got probably about 1,000 devices, I think.
Something like that, yeah.
Yeah, something. Talking into over various comms methods, LoRa, GPRS, Wi-Fi, even controls my home heating system. You can look at the slides and zoom in if interested, but So that all flows into the system, and then we've got a portal that allows us to look at the data. Because all it is just a complex way of getting there's been a face detected into a database, into SQL, and then we can mine that information afterwards.
Okay, so the overview of the demonstration is I'm going to add my face to the local database, and then when it's learned that, next time it sees it, it's going to recognize it and send a signal to the LoRa module. That's going to allow the door to be open, which in this case is represented by a flashing red LED, which is not that exciting, I know. And then we're going to send the LoRa message over from this device to our local base station and out onto the network, and then to our AWS console, and we can see, so to our IoT platform, we can see the stats in there. So internally, the MTMN library, basically what it does is it takes your image, it makes an image pyramid, and then puts it through a probability of a post feature net, works out which are eyebrows, which are ears, and throws away all the things that aren't interesting, and it tries to find 5 landmark features. In this case, it's the eye distance, your mouth distance, and your tip of your nose distance, and then it stores those away. And then when we come to run the neural net, when it's looking for new pictures, for new faces, it compares those stored ones against the ones that it's worked out.
And the important thing to remember is that this has all been done locally on a device that can run off a battery. I mean, I know, most people got iPhones or Android phones that's built into that, but the amount of processing power in your phone compared to what we're doing this on is quite astonishing. We're talking about something that will run off maybe a single AA battery for maybe a long time.
Okay, let's fingers crossed.
Yeah. Right, everybody, fingers crossed. Make sure
there's good vibes.
So I'll just quickly swap cameras, and I'll stop sharing the presentation briefly. Hopefully it won't go up, so you can see our camera maybe a little bit better. So we've got an iPad showing a video stream. Now, for this to work, we don't actually need the video stream, but it helps to demonstrate what's happening.
Can I see the kits?
So this is the board of the camera, which we showed earlier, which is around about £15. The one at the top with a little screen on is the one that deals with the radio side. And then if Andy shows the iPad, you can see Andy's face on the iPad, which is just showing the stream. So it just helps us to demonstrate what's going on.
Right, how's that work? So put it back. Get that there. Yeah. Okay, so if I put my face in shot, it should draw me a yellow box around it. Okay, so that means it's found my face and has reckoned that's a candidate for recognition. Now I press the capture button. Okay, so it's enrolled me into that. I'm ID 0, excitingly. So if I go away and come back again, I don't know if you can see the red light? So when it's recognised me, it's turned on the red light to signify the doors. Okay, thank you. Okay, the doors open. There we go. And if we were to look, if we were to point to Chris, so we're going to let's get this back on. There we go. It will go. Who are you?
Okay.
Can you see that?
Yeah. So the LEDs indicated that the door had been kind of activated and opened based on your thing.
Yeah.
Yeah. And then whilst all this is being done locally, so it's detected Andy, seen locally, turned the LED on, opened the door. It's seen me and probably set off some klaxon so that someone can come and kick me out of the building to try and break in or whatever I'm doing. It's been in the background queuing up the messages to say that this has happened, and those are now being sent over the LoRa network into our IoT platform. And you can see it flashing away, so they all get queued up.
Show this. Probably that's it.
No. So one of the problems with the LoRa network is that you're limited not only limited how much data you can send, but you're limited how often you can send it. Because it's free, and it's well, no, it's not so much free, because it's using an unlicensed frequency. There's a fair usage policy, effectively. You know, you don't want to take it over so that no one else can use it. So it's currently now streaming all that data out. Oh, all that data. It's like 20 bytes worth of data. It's not a lot of data. That says face 0, which was Andy, has been detected, and an alarm has happened, which was me trying to break in.
And just to kind of stress that all this is local to that device. There's nothing happening on any server anywhere.
No, nothing at all. We can turn off the Wi-Fi so that we haven't got the video stream, and it'll all do it locally. I mean, for real products, you probably have a little screen on there so you can see what's going on. But for our concepts, we can disconnect the Wi-Fi. In fact, it's not connected to our Wi-Fi. We have to connect to it, and it'll just still do the same job. It'll detect faces. It'll send out the messages. Hopefully, we can show you the messages that come in, just to prove that it does work. Just bear with me 1 second. I lost my mouse onto you can track on that. So hopefully you can see a web page. It's just got on the left hand side, it's got the faces that have been detected.
We're not seeing the.
Is it not working? Sorry, just bear with me 1 second. I'll share it a different way.
Sure.
I'm losing my voice now. Okay, is that better?
Chris Scope has started screen sharing. It's coming up, I think. There you go. It's on. Okay,
so yeah, on the left-hand side there, we've got faces that have been detected. So this is our dashboard into our IoT stack. So we've got the number of faces that have been detected and how often they've been detected, and then alarms. This is old data that we're using just to test it earlier. So if I just hit a refresh, you should hopefully see ID 0, which was Andy, jump up, and the number of alarms should also go up. Just decided it's not working again because it's doing the curse of the demo.
I assure you it was working earlier on.
Well, 2 hours ago it was definitely working.
Yeah, whilst that refreshes, so at the bottom there we can see, and this is just summarising it, but we get like the last timestamp in units time there, of which ID and the counts.
Yeah.
So it's sort of normal information that you probably want for a security system.
And what's the number of bytes? So I'm kind of interested in the kind of bandwidth, because all this stuff has happened locally. And what's the depth? Sorry, the height of data. So
with LoRa, it's slightly variable from 50 bytes up to about 120 something bytes per message that you can send out.
Right.
We basically all we're sending out here is a number and a timestamp. So we're probably sending 5 bytes at a time.
Yeah.
There's a bit of wrapping that needs to go around that to make it work, but you're probably talking at most 20 bytes on these messages that are going out.
Yes. Yeah. That's good. And just so that you know, guys, I think your profile screen is frozen, but we can see the data on the screen.
Okay. Yeah, I'm not so sure what's going on. It's all gone wrong.
always does when it's live. But that's great. I mean, I'm pretty amazed that literally, I mean, we're talking bytes of information and everything done locally on that device.
Well, that's the beauty of putting the sort of AI at the edge. I mean, you don't need that backhaul to get all that data out to do the number crunching somewhere else. You can do it locally on a battery powered device that can run months off a lithium ion battery, and make these decisions locally without the link. So especially things like a security device, or if you need to make a decision quickly that something's going to happen, you don't want to rely on an intermittent connection, as we've shown here in the demo. You can't afford that. And then if you needed that link, then it costs quite a lot of money to keep that link there for when, for most of the time you wouldn't need it.
Yeah, wow, excellent. Thank you for that demo. It's good to see the kind of real life example of it, and also the hardware, which to see the face recognition occurring in real time,
And also that was we put this demonstration together in less than a day. So you can see that the tools and the libraries and the data sets you need to do for learning, for doing the training and stuff is all sort of freely available and quite easy to use.
Brilliant. Okay, excellent. And I'm also curious around the libraries that you use for the AI in this. I think you kind of presented it earlier on, but these are readily available as well. So they're almost plug and play now, would you say?
Yeah, ish. So because, as Andy says, we threw this together, we used an open source project called ESP Who, which has got an ESP face library in there. Now that it's based around someone's PhD, I think. I think we've got a link to it later on in the slides. Sure. But there's lots of different ways of doing this. There's a big one is quite popular is the Tensorflow system from Google. And they have a thing called Tensorflow Lite, which is we'll talk about actually in a second, which is it takes the models that have been designed to run in the cloud, and then some of those it can distill down into a small library that you can then put onto these devices. Because although we've got a lot of processing power, we haven't got a lot of memory or flash to store some of the information. In the cloud, you've got terabytes worth of data. It's just a case of pressing the button, you get some more. Whereas on these devices, you haven't got that luxury.
Yeah.
So you have to take the complex models, run the maths, do all the training in the cloud, and then download a sort of cut down version. It's just basically it's distilled down to the bare minimum to still do the job, and it does the job quite well, as hopefully we've just shown.
Brilliant, thank you.
So I've got a slide here, which is the typical flow of how you would do this. So the first thing is to capture your data. So say, for example, we wanted to record woodpeckers in a wood or something. We'd have some sort of audio or vibration sensor, and we'd attach that to some trees, and you would capture a load of data. And then you would then have to sort that into data that was real woodpeckers, and you'd have to sort out the data that was things that maybe sounded like woodpeckers that weren't woodpeckers, or they were like tractors or whatever. So you'd have two piles of clean data, stuff that you want to detect and stuff that you don't want to detect. Okay, then it's the tricky bit right in the middle of this flow diagram. So you've got to choose a model, and then you've got to train that model, and then you've got like an iterative process where you give it the data, you let it learn, you let it train, and then you predict the output, and you're looking for the results to converge to the answer that you want. So that won't happen the first time, and you'll have to change the amount of nodes in the middle, and the topology of it, maybe the way the data is gathered. And it's so you keep on going down that loop until you found a neural network topology and size and shape that works for your application. The tricky bit. Okay, once you've got that, then you can convert the model into code. So different things do this different ways. With TensorFlow, you've got a Jupyter Workbench doing it in Python with some cloud access, I think. The STM Cube AI stuff is all online. So you upload all your data, your cleansed data up onto a cloud, and it generates you I think a header file from that one. So it's an iterative process, and basically in the end of it, you either get a header file or a C file, which you can then link with your application library to perform the neural net that you're after. Then when it's deployed into the system, you then inject the same go, no-go data and make sure that that matches what you expected when you were running all this on the PC when you're doing training. So a lot of the time, the way that the data is captured on the embedded system is not quite the same as it is in real life. So maybe you've got to go back to the middle process in this and do some different quantization of your input data and some more learning. It's quite iterative, it's quite time consuming, but once it's done, you have a model that's trained and is good for purpose.
Yeah, I mean, the workflow is very similar for traditional AI systems, isn't it? It's just you still need to, obviously, capture the data, train the model. The only difference is that when we talk about embedded is that there's that extra step, isn't there, where you've got different mechanisms of capturing the data that will differ. You can always guarantee that you'll have to go around this 3 or 4 times.
Yeah, and it's running in a different environment. So, like I say, a real-time embedded operating system is a different environment than Windows or Linux or whatever you've done your training on. So there's those differences. Yeah.
So we've got a question here from Ilya around. I think he's similar kind of curiosity to me. So once the system's deployed out into the kind of field, and you want to reconfigure the system to not maybe recognize whether it's Andy or Chris, but recognize if they're male or female, for example, just as an example. I mean, what does the hardware need to stay the same? Is it just completely soft upgrade?
It depends, is the answer to that, I think. I mean, something changing from faces to sexes, whether male or female, or looking at heights or whatever you want to do, because it's still visual, the hardware can probably stay the same, obviously, because all you need for that is a camera. And then you just have to download a different model, maybe, or different training data. And that can be done over the air.
Right. And what size data is that? Sorry, I mean, so if you're going to upload a new configuration,
we're talking a few hundred K. We're not talking massive amount of data. I mean, the model, the code that's actually running. Well, I suppose unless you're changing it drastically, and the model can stay the same, and you're changing weights, the feedback weights.
Yeah.
That's not so bad. We're talking a few hundreds of K. But you could have it so that you could change the complete model. If you did that like in shared objects, you could swap that different models out in real time, on the live system. We've done that before.
Brilliant. Okay, so hopefully that answers your question, Ilya. That was a good one, because I was thinking the same thing as well. How you upgrade, if there's a new kind of configuration or requirement around detection,
Yeah, I mean, part of that then just comes into the sort of normal way of updating an embedded device in the field. Because you could just send it down as one big binary blob, which we'll actually come on to in a little bit in a second, because it's a big problem in embedded remote devices that have got a sporadic connection.
Yeah.
So yeah, it's the same mechanisms that you use to update anything, really.
Yeah.
So we showed you the proof of concepts in our little process. So these are just what we would do after this once we've got proof of concept. Now we gather some metrics, help us with whether it's feasible, what changes needed. It helps to feed in to the requirements, which would be the next step of getting proper defined design requirements for the system. And the important thing is that we make sure that we've captured and thought about any security concerns up front before we do any real development on any system.
Yeah,
it's a big problem. Traditionally, small, low-power devices have usually had no security on them whatsoever. It's a big problem. There's hundreds of thousands of IoT devices out there that are open to the world.
Wow.
So you need to be really careful, and especially for, as we've shown, a little security device, you don't want any way of getting in there and adding my face, for example, if I'm not supposed to have access to whatever it's protecting.
Yeah, or just open.
Yeah, or just open the door. Yeah. But the important thing is, because we get all these requirements up front, written down, specified, we'll look at the security problems, look at attack vectors and how we can mitigate those. We'll have a document that's got all the design, all the requirements written down, set in stone, and then what we develop will then be for that product. Exactly. You're not going to get any surprises, hopefully, and there's always changes that need to happen, but they can be managed as the project goes along. There's a lot of information on here. This is just an example of a full project life cycle from someone having a design idea down to the bottom here of manufacturing it. We could go into it if anyone wants to. But I think Tisha shared the slides.
I was going to share them, but we'll share them afterwards. Thank you for that. We'll make sure that guests get that. Thank you.
Yeah, so this is the sort of thing we would do for a customer when they come in and they want a product developed. just mapping out all the different processes that need to be done through to as far as they want to go, either production or end of proof of concept. So just an example, just to show the kind of thing that we would normally do. We've talked about security, so we did a slide on security concerns. Do you want
to? So as I said earlier, that these sort of low power devices, traditionally there's not really been much thought put into security. Now that is changing. The issue is that you usually have to cook it yourself. There's no standard way of doing this. The OSs, although they're getting better, they don't have things built in. Processing power traditionally hasn't been there, so you can't do things like encryption on the fly or strong encryption on the fly, although that's changing as well. And the hardware that's now coming in has some of the hardware blocks that do this functionality for you. So you can get an encryption engine in some hardware, but it takes the burden off the software, the processing side, which is really good. I mean, there's things like the ARM trust zone. There's anti-tamper devices mechanisms going in there. So it's getting better, but it's still pretty much in infancy, I think, security-wise. And then another problem is we're talking about a device here that's battery powered and is basically at the end of a really unreliable data link. So getting things like software updates or downloading new training models can be problematic. And again, there's no real standard way of doing that. So you need to make your own. And if you're making your own, you're open to adding in security vulnerabilities because it's not tried and tested. So these are things that you need to think about when we're designing these systems up front, make sure we get them right. There's no sort of standard library for doing any of it, unfortunately, yet. It's getting better.
Yeah. And I think I'm glad you mentioned the security, because this is one thing a number of our guests on the CTO Confessions kind of podcast series have mentioned, that security is very rarely brought into at the beginning of a project. It's always an afterthought,
Yeah, and it's really, really difficult to retrofit, because if you're retrofitting security, you need a secure way of getting that retrofit into your device. And because the device has got no security, it's open to compromise. So it's sort of a vicious circle. Yeah, so you need to think about it up front. You need to make sure that the basics are covered and it's as secure as possible. I mean, one of the good things about LoRa is because of how it works, there's a very, very, very small window of attack from the wireless interface. It sends out a message, and then you've got 2 1-second windows when you can actually send the message back in. And all the data, as I said, is encrypted end to end. It needs to be signed to come from your application. So it's actually, from a attack vector from our point of view, it's actually quite good. And it's that low bandwidth that you can't really do any damage, that probably wouldn't be seen. But because it's low bandwidth, again, it's an issue of getting updates into the devices.
Brilliant, excellent. Yeah, that's good. Thank you for kind of mentioning the security thing. It is an important subject. It's always. I've worked on projects where it's always the afterthought. But
I mean, some of these things, I was saying to Andy earlier that we've got 3D printing. We use some open source software for it, and someone has just done a research project. I'll dig out the link where they've done basically a search, and they found a lot of 3D printers that are open to the world. So you could do all sorts of damage. You could print things that you don't want print, or what you could actually do is break the firmware in the device and set fire to it, and potentially, because these things have got heaters in, they get up to 280 degrees. If you turn them on, turn the fan off, it's not going to do. It could cause a fire. So these are connected to things that could potentially do damage.
Yes.
Hopefully, it wouldn't be. I mean, that's a bad example. You can set fire to things, but usually, you see cameras. One of the big things is like people looking at cameras because they've left them open. And they've all got a default Wi-Fi password or admin password, and you get people snooping around looking at your cameras. And child cam monitoring is a big one, isn't it? Where people have hacked into them and been talking back to your child because you've got an IoT device that's open to the world. So
you need to take it seriously.
Yeah, definitely.
And we try and insist on every project just to try and get these things in straight. and like trying to enforce that this is the most important thing they're going to be, because the companies are responsible for their own security, and our responsibility is to make them aware that they are. So.
Yeah, and what I love about this system of bringing the kind of, there's less information flowing between. It is some more secure inherently, because you're not throwing lots of data around. It's all kind of localized, and I think you mentioned earlier on that all the data in the memory can be encrypted as well. So the device is kind of pinned down.
Yeah, and it's anti-tamper devices. So if anyone tampers with it, you can get it to automatically erase the data. So there's no way, if you do manage to get physical access and pry it open with your screwdriver, by the time you've opened it up, it's erased itself. So there's nothing in there anymore.
Yeah. I mean, you can go to the end. I mean, it depends on the application, doesn't it? I mean, some things are going to need this kind of like stuff, because stuff is really, really important that it doesn't get tampered with. But
yeah,
there's always a basic level of security you need to add.
Yes, great, thank you.
I think that's Q&A then.
Yeah, that's good. So have we got any questions? Have we got any answers from the audience? Questions and answers. Have we got any questions from the audience for Andy and Chris before? We've got about 7 minutes left on the webinar.
One thing to talk about, actually, which is not in the slides, we probably should put in, is about where this can be used. Where you can put AI at the edge. I mean, there's a lot of things that we've been looking at recently around healthcare, manufacturing. Manufacturing is a good one, because you can make a device learn, for example, how a machine normally works. So you can have a sensor, say, on the side of a machine that's listening to how it operates, looking at temperatures, sensing vibration, and then because you can put the artificial intelligence in there, it knows the norm. It can detect when it's gone out of spec. So if a bearing, for example, starts to go wrong, you'll get some harmonics that aren't normally there. So the device can be doing this locally and say, there's something not quite right here. Send a message, and you can send out a maintenance engineer before it actually goes wrong.
Yeah. That's quite an interesting one. When engineers, when they listen to an engine or listen to a machine, they can tell there's some kind of intuition there, I guess, without actually knowing the detail what's happened. They get there's an indication that something is about to kind of do one.
And say also, if you're in a warehouse and you've got a device in there that's monitoring, say, the guys in the forklift trucks driving around, you can say, well, this guy's driving around too fast, or he's done something wrong. So you can look to see what the normal behaviour is and learn that, and then you can flag up bad forklift truck driving or whatever.
Yeah, I mean, it's similar to the healthcare, isn't it? You can have, for example, if you've got an elderly resident who living on their own, you can have a system that detects their normal behaviour patterns, and then also figure out that something's not quite right. They've not woken up at the sort of normal time, or they've been in a room longer than normal. They can ping a message so they can send help before, without them needing to do that themselves. And
I guess
little things like that.
I guess there's a kind of another dimension to this, is that it doesn't just have to be about visual. It could be about sound. The sound of somebody falling down, a thud. It could go.
Also, been looking at voice stress analysis as well. So if you are monitoring, say, like a phone call, you can start to pick up when people are starting to get more stressed on the phone. So from a customer service point of view, you might want to pass it on to a manager or that sort of thing. Looking at that. What else have we been looking at? We're looking at crowds and seeing if there was some sort of agitation going on in crowds. So there's a normal sort of flow of people at a train stations, and then something goes on, the pattern of people changes. So that kind of thing as well we've been looking at.
Yeah, there's lots of I mean, especially around automatic auto piloting cars and things. And it's probably even just detecting the flow of traffic. It's detecting the abnormal from the normal. It's where it's probably quite useful, because you can make a decision real time, quickly, act upon it, and then deal with actually storing the data in the background. And once that's happened, then it's not so critical anymore.
it reminds me of, you know, for example, the App Store. You know, there's a democratization of the ability to kind of do this, and the use cases are just. It's not so much about the technology and about being able to do AI. It's more a case of what do you want to do with it. You know, that's what I find fascinating. Is, you know, I mean, there's loads of use cases that are just spinning through my head right now. You know, where it could be done locally. There's no need for a network of information. Just do it locally. Indicate.
There's a lot of things as well where you think, oh, perhaps we need some AI to do this, but you could actually just do it in sort of traditional, just reading the sensor and comparing it with value. So you need to.
Yes.
Need to be careful. It's not just something I just slap this onto every single project I ever do. You know, for example, if you're monitoring the temperature in the fridge, you don't really care so much. You may be able to actually detect when it's about to go wrong. I mean, the power systems are probably a good one for that. You can look at what's actually happening on the network, can't you, and detect when it's about to go wrong before it goes wrong. But if you're protecting the fridge, you just probably want to know that the temperature's gone below or above.
And it's got beer in there. That's all you want to know. You know, it's got beer in there. So thank you for that, gentlemen. We haven't got any more questions, but I've really enjoyed that demonstration. Hopefully the audience has as well. It's brilliant to see how this technology has kind of moved on, and I think Felix, who's on here as well, he's an AI expert as well, and I think you'd be glad to hear when you mention the fact that not AI isn't the solution for all of this. Sometimes you can do kind of more simpler machine learning or maybe some kind of algorithm, you know.
Yeah. We'll put some links on the last slide if anybody's interested, just of TensorFlow and the ST micro one. Is the workflow on that is very, very good if anybody wants to look at that.
Brilliant.
And also to the one we're using for this face recognition.
Excellent. So thank you all. Thank you to the audience as well for joining us. And yeah, I look forward to maybe doing some embedded software development with you. You know. No.
Not again.
So thank you very much, guys.
Okay.
Cheers.
Thank you.
Bye.